Today on Earth Focus, melting Arctic sea ice and what it means for you. Dr. Julianne Struve on how the changing Arctic will impact global weather. Coming up on Earth Focus. Arctic sea ice is melting faster than predicted, and a project supported by the National Science Foundation and the National Oceanic and Atmospheric Administration finds that greenhouse gases are part of the reason why. Julianne Struve led the effort.
I knew the importance of snow and ice in helping regulate the planet's temperature, and it's one of the reasons I went into studying snow and ice, because it's very important to our climate system. I don't think it really was until about 2002, 2003 that we started to really start paying attention to what's happening in the Arctic. Because before that we would have, we'd have low sea ice years in the 1990s, and then they'd be followed by a high sea ice year. But what started happening in the 2000s is you'd have a low sea ice year, and then another low sea ice year, and it just kept happening year after year. And that was something we hadn't seen before, at least during the last sort of 50 years of data collection. And then when 2007 happened, where you had 26% drop from the previous September in 2006, and everybody was like, what is going on? Because nobody expected that large of a drop. It took everybody by surprise in the science community. Well, the rate of decline right now over the last 3 decades is about 14% per decade. And this is actually faster than most of our climate models are actually capturing today. These projections of ice-free dates of like 2050 to sometime beyond 2100, it looks like it could happen a bit sooner, so like 2030 might be a more realistic date as to when we might see no sea ice in the summer in the Arctic. Basically everything on the planet is connected. And the Arctic is sort of the big refrigerator for our planet. It helps keep our planet a lot cooler because, as you know, snow and ice reflect most of the sun's energy that comes in during the sunlit period. So if you remove the snow and you remove the ice, then the land can absorb that heat from the sun, or the ocean can absorb the heat from the sun and warm up further and amplify the warming in the Arctic, for example. All of our weather systems, our large-scale weather patterns, are driven by that temperature difference between the equator, which receives most of the sun's energy, and the polar regions, which receive very little of the sun's energy. But if you change that difference in the temperature between the two regions, you change the speed of the large-scale weather systems that move around the planet. As you change the temperature gradient, these weather systems start to move more slowly through our atmosphere, and you can get more extreme conditions such as droughts and floods that just last longer in a particular region because these weather systems are moving that much slower. And so there is a connection between what happens in the Arctic and weather in the lower latitudes. And we knew that if the planet started to warm and you start melting snow and you start melting ice, that you're going to have this sort of feedback effect that's going to amplify the warming, because you're going to warm up, you're going to melt more snow, you're going to melt more ice, it's going to further warm everything up and melt more and more snow and ice. So you have this really vicious positive feedback loop. So we knew that the Arctic was very sensitive to increases in temperature, and it's responding like you would expect it to as the temperatures have warmed. So it is sort of our early warning system. We did expect changes to happen first there compared to anywhere else on the planet. We looked at the factors that we tended to use to explain past low sea ice years, and those factors really weren't working anymore. So it wasn't necessarily a certain weather pattern or a certain temperature pattern that was causing it. There was some sort of a background forcing that was happening on the ice cover that we were trying to figure out what that was. When I started looking at the climate models and comparing them to the observations, then I started realizing, well, all of these models would be in their own phase of natural climate variability, so they could be showing increases or decreases over a period of observations. But they're all showing a decrease. And so that starts to help implicate greenhouse gases as forcing the changes that we're seeing today in the ice cover. We can say that about 50 to 60% of the loss of sea ice that we're seeing today is a result of greenhouse gases. The other 40 to 50% is actually natural climate variability. So we know both are acting on the system right now. And right now the results are about 50-50, I think, in what's happening with what we're seeing today. The planet's going to warm by a certain amount of degrees. The sea ice is going to disappear in the summertime. The ice sheets are going to continue to respond. Sea level is going to continue to rise. But when we look at things like, well, where are the precipitation patterns going to change? Who's going to get more rain? Who's going to get less rain? What's going to happen to the American Southwest? Are we going to lose our snowfall? In that sense, there's not a whole lot of robustness between the model simulations yet. So they give different answers in different regions. And so we don't have a good handle, I think, on how rainfall, for example, is going to change in a warming climate. And that's really, I think, one of the key things that we need to better understand is where is the water going to be? Because a lot of regions depend very strongly, for example, on a glacier to feed the city and provide all the water for a city like Santiago, Chile, for example. And so better understanding of how precipitation is going to change and snowfall is going to change is one of the key things that we need to understand. We do see that if you run climate mitigation scenarios and you reduce the amount of greenhouse gases, that you can actually bring the ice back. You can stabilize the amount of ice loss. If we were to reduce our greenhouse gases, it's not going to be this runaway effect. We can stop some of these changes that are happening in the Arctic. But that does mean we're going to have to commit to reducing the amount of fossil fuels we're putting in the atmosphere. And that's the real challenge.
Airwaves, a global channel of uncompromising stories, world news, documentaries, entertainment, and culture. Link TV, connecting you to the world. For more information, visit linktv.org.